Pretty interesting topic today. So let's talk about charge pumps. I was thinking about what's the best way to teach it, and I just found the notes from last year. I just this is really good instruction. I wrote it last year, but I couldn't remember anything about it. So it started with the voltage doubler. That's a really good way to teach it, I think. So the goal is to boost the voltage from. And if you look at the examples, they are usually a 1 volt and they are getting boosted to 2 volts. And how that works, so it's using capacitors and put them in series. For example, you got one cap, you got another cap, plus minus, plus minus. So you can treat them as two batteries in series. So it's getting voltages boosted that way. If you ground here, so it's a constant ground, 0 volts. So you're adding one more voltage in the middle. Definitely you are able to double the voltage. And you may have learned the voltage doubler in analog. Have you? No, not yet. Okay, so that's basically the circuit that I used for the ionizer circuit. I just used the multiple stages instead of doubling it. I probably multiplied the voltage by a factor. So it's not a voltage doubler anymore. It's a voltage multiplier. That's the easiest way that you can boost the voltage from like 20 volts to a few thousand volts on the PCB board. So before we look at the circuit of the voltage doubler, I'm going to draw a circuit for you guys, and you will tell me what is that circuit is. Okay. Are you all in analog or just the two of you? Okay. If you got a voltage in here, so what is that circuit and how that works? What is this code? What's going to happen if you have a voltage swinging from like -1 volt to 1 volt, for example, like this? Yeah, it's a rectifier, but what's the name of the rectifier? Yeah, half wave. Half wave, not bridge. Yeah. Half bridge is a robotics tool, but you are not in robotics tool. That's interesting. That's a Wheatstone bridge that we used for the string gauge. Excuse me. 麻烦了，我上课呢。行，就这样啊。拜。Half wave rectifier. It's being used in the power supply circuits. And so when the sine wave comes in, if it's positive, which is larger than 0, okay, so the voltage can pass through that diode. We're considering the diode is ideal, so it's not having a 0.7 volts drop from anode to cathode. Okay, for this, if this is V in, right, this is V out. For the first half, no problem, it's going to pass, right? The first half, it's going to pass. So the capacitor is just used as a low pass filter, just holding the charge. Because you are connecting the output on the top of the capacitor, so we don't have to really worry about this for now. Okay, so the first top is going to charge up the cap through the diode and charge up the cap. So you are receiving exactly the same voltage. You are not having any drop from here to here, which we're ignoring that 0.7 volts drop, right? Okay, so what about the negative 50%? What's going to happen? Yeah, cut to 0. It's not going to pass. Okay, if you have more, this is just one period. There might be like many, and then you are having all the little bumps. So the output looks like just a bump and 0 and bump and 0, bump and 0. Okay. However, the capacitor is if you have a big capacitor and your frequency here is fast, so you are not able to charge and discharge this capacitor fully every cycle. So it's being so the output will be filtered because the capacitor is served as a low pass filter. High frequency will pass, but low frequency will low frequency will stay. But high frequency will be attenuated. So if this is considered as high frequency, right? So eventually it will be not able to be discharged to the bottom, and then it starts charging it up again, and then discharge and won't be able to reach the bottom. But you have to modify it. If you use a pretty small capacitor, definitely it will be able to charge and discharge fully. Now the big capacitor, so it has a huge delay. So that's why it doesn't have enough time to discharge to the bottom. Then it starts charging up again. So eventually it's filtering this out, and you still have a little, this is called a ripple. Okay, so still have a little ripple, but it's very close to a DC voltage. Eventually, this half wave rectifier will stabilize the voltage at something similar to a DC voltage. All right. So if we rotate or we swap the position of the capacitor and the diode, you make it this way. It can be a sine wave, can be a square wave, doesn't matter. So let's use a square wave. It's easier to generate in digital circuits. 0.5 volts and negative 0.5 volts, for example. Right? As an input, as a V in here. It's very similar, exactly the same components in the circuit, but different positions, different locations for each. And what's going to happen to output? This will be a totally new way to analyze the behavior of the cap compared to the way that you did in circuit 1. So basically, you just use all the differential equations to run the calculations for the nonlinearity of the cap. But here we don't do calculations for now. Okay, we just think about the charge movements. So, for example, at the very beginning, before anything getting injected into the voltage in, right? We're having a 50% of the period, which is 0.5, negative 0.5 volts. And this is grounded, keep in mind. And you're adding a minus plus 0.5 volts for this period as a DC voltage. You turn it on, so it starts pulling charge from it. I know it's DC, it's kind of difficult to understand why capacitor can pass DC. But is it DC? It's not. It changes from, there was a high voltage and then it goes down to negative 0.5 volts and it will change later. So it's swinging, okay? But if you give a constant DC, it will have enough time to charge up the cap and will be stabilized. But this is swinging or oscillating all the time. So it's not DC. Okay, so for example, you turn on a switch and add a negative 0.5 volts to these two nodes. What's going to happen? You just add this voltage to it. So before there was nothing. Because we are looking at the sort of like instantaneous response of the cap, so the charges are moving because it's not being stabilized, because it's not DC voltage. That's why it's not being stabilized. So we are looking at the movement of the charges. Right now you have negative voltage being added to it, so that you can consider that the current is being put out from the cap. Okay, then what's going to happen? So this plate is losing its current. We're only looking at current. I know you can look at the electrons as well. But let's just keep it consistent. We just look at the current for now. Okay. So current means it's positive charges are moving. I know it's weird. No positive charges are moving, but just consider positive charges are moving in the direction of the current. Okay. So when you add a negative voltage here, it's going to pull positive charges to that direction. So leaving negative charges here, right? Just pulling things out from the plate. It's going to form an electric field because negative charge will attract positive charge on the other side of the plate. Okay? Does that make sense? So you have to think about like it's pulling, and if you swap the voltage polarity, it's going to push charges into the plate. So it's dynamic, it's not static because it's not DC voltage. So DC voltage, it only happens when you turn on and turn off the switch. But now this is always on and off, on and off. So that's why it's not DC. Okay, so now you got a negative voltage at the very beginning. It's going to pull the charges out and forming a plus and minus. So this looks like what? Yeah, it's a battery. So what's the voltage of the battery eventually? It's going to reach what? No, eventually after it's being stabilized at this voltage for the input. But if you look at this plus minus, it's going to be 0.5, right? It's going to be 0.5 volts. So you are forming a little battery across the cap, which is 0.5 volts. Okay, so next we will go up at a time point. It's going to go up to 0.5 volts, positive 0.5 volts for a while, right? What's going to happen? So it's going to flip the voltage polarity and change it to plus minus 0.5. Okay, so now it's like exactly what I just drew here. You got one cap, you got another battery, which is the power supply, adding to it in series. Okay, so eventually the voltage here at the output compared to ground becomes, you're thinking why this is not changing the charges over here, because there's nowhere to go. You see, this is blocking the charges to go to ground. Okay, it's blocking. So what's going to happen is when you flip the voltage polarity here, it's going to add that voltage to it instead of canceling out the voltages. But what's the voltage across the capacitor after this polarity change of the power source? No, across this one. So before you flip the voltage, it was 0.5 volts across the two plates, and now you add it to it, and VL becomes 1 volt compared to ground if you probe it, use a multimeter. But however, the voltage difference between these two is still 0.5 volts. So the only voltage changes the voltage potential here becomes 0.5. So 1 minus 0.5 is still 0.5 across the two plates. Okay, so after one cycle, it's oscillating pretty fast. So you have to know that, be aware of that, the voltage multiplier won't give you a 1 volt output at the time that you switch it on, right? It takes like at least one cycle to charge up the cap and boost it to 1. You need at least one period. But that doesn't matter if you're using this circuit as a voltage generator. You turn it on, it's oscillating like 1k hertz. It's just a 1 out of 1k periods. It's done. So it's less than like 1 millisecond. You are getting that high voltage output. Okay. So it takes time to charge it up. This is the ideal case, but a lot of times if you have a big capacitor, it won't reach that 1 volt in one cycle. It takes a few cycles to charge it up. Eventually, it will reach that voltage. So what if it comes back to negative 0.5 volts again? What's going to happen? So it becomes negative plus 0.5. What's the difference between this state and the state here? So ignore anything else. Just ignore whatever I just told you. Just by looking at the circuit, and not so I used to have 0.5 volts across the two plates, the cap, and now I have 0.5 volts from here to here. So what's the voltage at V out? If I have a cap, another cap, or two batteries, whatever. So this one is this cap is this guy, for example. It has a plus minus, and this is output. This is ground, okay? And now I flip the polarity of the voltage. I'm having this. We know this is 0 volts, right? Okay. Because the power source is giving you this plus minus this voltage. This from power source is ideal. Okay, you cannot change it. So 0 volts, there's a 0.5 voltage drop from here to here. So what's the voltage here? And there's a 0.5 voltage getting boosted, right? Increment. So what's the voltage here? Yeah. Okay. And then you flip this voltage again because it's oscillating, right? What is the voltage at the output after that 0 volts? Whenever it's, yeah, going to 1. It's going to oscillating from 0 to 1 instead of negative 5 to negative 0.5 to 0.5, right? So this will be changed to this. They are saying the oscillation amplitude or overall is not being changed, right? You got 1 volts peak to peak, and you got 1 volt peak to peak as well here. How you are claiming you are getting a voltage getting boosted? What else you are missing here? Look at this example. The goal is to get a high voltage, high DC voltage. What else I'm missing? During the filter. Okay, if I had a filter, what's going to happen? So previously you had a 0.5 to negative 0.5 to 0.5. So if you filter it out, you are getting something like this. There will be a ripple, right? So it's going to be around 0.5 volts DC, right? But now you got a 0 to 1, and you filter it out, it looks like this. It's going to be 1 volt DC. You're having a boosted DC voltage, right? Can you add more stages to it to boost the voltage even further? Yes, you can. That's the circuit called voltage multiplier instead of a voltage doubler. So let's start with this. All right. And then you have to filter it. So if you ground this pin, for example, we have an input voltage which is 0.5 to negative 0.5. And we're assuming that the filter is perfect. What is the DC voltage at this point? Yeah. And next, we use this point as a ground for the next stage. And then we build another, the same circuit as this part, but we based on the voltage here. Is that going to work? based on the voltage there, and the swing is still from here. Where is this? Yeah, I think we have to draw it like this way. So got another stage, you need a cap, and you need a diode, but your ground is not 0 anymore, your ground is 1, so it's based on 1 instead of 0. And then you filter it one more time. Then just keep going. I'm not sure if I should connect it here. I think so, because it's the only place that you are getting oscillation. Yeah, I'll double check and let you guys know on Wednesday. But this is not the topic for today. Since right now you understand how the voltage are adding to the getting added to the capacitor, and we should move forward with the charge pump. Okay. What's the max voltage you can get from here? Right? Is there any question about this concept? If you don't know how we get this one, then you get confused a lot by looking at the charge pump circuit. So VDD, VGS, when this one dump charges, if I have a cap at the load here, dump charges to the cap, okay, start charging it up. Whenever it reaches VDD minus VTHN, it shut it off, because here's VDD, and this is G, this is S, so VGS becomes VDD minus VTHN, which is exactly VTHN. So if this one is getting larger, it's going to shut it off, so it won't get larger. So it's going to stop at this voltage across the two plates of the cap. So so the current is being dumped from the VDD to the cap. Is there a way that you can conduct the current from bottom to top if you have an NMOS connect this way? Can we run current that way, and why not? Because we can definitely run current this way, no problem. We have demonstrated that the highest voltage you can get from the cap is this. So can you run current that way if you add a VDD here, for example? You have a high potential here, like VDD. Can you charge up a cap on the top?
No.
Can we? Not as forward biased. NMOS forward biased. NMOS forward biased. What do you mean by forward biased? We've been talking about the forward biased diode, right? But why NMOS is? But what's the easiest way to understand that the current is not going from bottom to top? If you're running current that way, you consider this is Jesus S. What is VGS? Yeah, lower than VTHN, right? Okay, so it's not going that way. So a lot of times this type of connection is called diode connection, because it performs like a diode. If you have a NMOS have a drain gate connection like this, right? It works like a diode. And a lot of times people started, being interested in using a lot of the MOSFETs instead of diodes. I think part of the reason is they can make the transistor very small using the channels. But the diodes have to form a p-n junction. There must be a lot of limitations on that. So they are trying to use capacitors using these ones and forming diodes using NMOS transistors. And so if you connect NMOS, so these are the drain and gate, right? The drain and source. Okay. If you connect it this way, it's a capacitor. How that works. If you look at the cross-sectional view of the transistor, and you are shorting, if you are shorting drain and source, you are basically shorting these two, right? Okay. And you got a gate. You have a cap, sort of, because there's a oxide in the middle between the gate and the substrate, or the diffusions here. So you get a one plate. It's not metal, it's poly, but it's one plate, another plate. You don't really care about the shape of the cap, as long as it stores charges. Why do you care about that, right? And it can make a huge. If you make a huge transistor, it's going to be a big capacitor. And what you need to know is what is the parameter in here, which is called cox prime, cox prime, which is the it's a constant based on the process of the manufacturer or the technology. And you have to use the cox times W times L, which is width times length, which is going to be the area of the channel. It's basically the area of in between here and here, right? It's like the capacitor's area. Okay, because these diffusion regions, they have a direct connection to the channel. Okay, so they're connected to the channel, even though they don't have an effective overlap between this diffusion and the gate, but because they are connected to the channel, and the channel has an overlap with the gate, so you can form a capacitor by using a transistor by connecting EMS together. And this is the parameter you can find for most of the process. If you get the technology design kit, usually they will give you that parameter. So you have to times the area. So this is probably one, I don't know, but they must have a unit for this parameter. So you just use your area times this parameter, you can get the oxide capacitance. So that's the oxide layer capacitance of the oxide layer. And here we are using the NMOS transistor to form a diode. Okay, since we can boost the voltage using diodes, right? By doing the voltage multiplier circuit, so we can definitely replace the diode by NMOS transistor and to boost the voltage in a similar way. Now let's look at how we draw the circuit. Charge pump. So very similar concept. Okay, if I have a capacitor, they are connected to the input and a diode on the top, and connect to VDD, and that's V out, and that's V in. Because the digital circuit, basically they are swinging from 0 to VDD. You're not getting negative voltages. Okay, so it's going to be a 0 to VDD oscillation. So that's the circuit. What is the V out? Based on the operation of the voltage doubler we just learned. What's the difference between these two circuits if we look at the two circuits? Since we already know how this works. To find out, first you have to connect the capacitor to the input. Okay, same thing. But here, instead of connecting that to ground, we have the anode shorted to VDD instead. What's going to happen to the circuit? Because this is being forward biased, So it is able to charge up the cap that way, right? So when you give a 0 volts, if you switch it to 0, you're actually pulling charges from here to here. It's an AC signal. Keep in mind, capacitor can pass AC voltage, right? It's going to pass exactly the same thing. But how it passes the voltage, it's a dielectric material in the middle, right? This is another, one more time, I hope you guys can understand this intuitively instead of thinking about the nonlinear equations. If I put a sine wave, you can run the LT SPI simulation right now, okay? If you get a sine wave like this, and you are getting a sine wave here exactly the same, even no phase shift. Why? So you were told that capacitor is passing AC signal, right? We're told that in circuit 1. You remember that? Yeah? It blocks DC, but it passes AC. But is it really passing AC? Or it's just alternating the electric field in between the two plates and indirectly passing the same signal here? So for example, you are looking at the first half here on the top, right? So that's positive, and it's going to push, it's going to dump charges to the cap, to one plate, right? And what's going to happen to the other side? Because yeah, current. So we've got a current running in here. So when you have positive charges being dumped into the plate, it's repelling positive charges the same way, right? Because the positive charge will attract negative charges to it, which means that positive charges are being expelled from the other plate. So that's why if you have this current, it's going to be converted or transferred to the other side exactly the same. It's the same way, expelling the charges away from the plate. Okay, so same concept here. So if I'm pulling charges away, and on the other side, it's going to dump charges to the other side of the plate. So if we replace this diode with the gate drain shorted transistor, because we know this works the same way as a diode, okay? What's going to happen? When you have a 0 volts, or switching that, because you turn it on for a few times, right, it's going to oscillate really quickly. So when it switches, before this one is getting charged, so the plate doesn't have any voltage across it, okay? The first cycle, it jumps from here to here, right? So it's going to discharge the cap. It's going to pull charges away. So it's going to dump, VDD is going to dump charges to the other side of the plate. So what the voltage here will be eventually after this cycle? After this cycle, what is the voltage here will be? It's not a constant 0. It drops from VDD, okay? It's going to dump charges to it, right? Until when? So if you look at these circuits, you can have exactly the same circuit like we drew here, right? You got a cap, you got a diode connected transistor, you got a capacitor, and this is ground because it's being pulled down to ground. You got a NMOS, you got a capacitor, you have a ground. So when it dumps charges to it, what is the voltage here will be? Yeah, so here it becomes VDE minus VTHN. And now the cap's different from the one we just analyzed, because this one is getting a charge on it. Previously, it was just neutral. It doesn't have anything before you turn it on. So now you have plus minus, okay? And the voltage here is, voltage across it is VD minus VTHN, all right? and then it's getting switched to VDD. What the voltage here will be. So what's the voltage across this cap? It was VDD minus VTHN. And now you add another VDD to it. It's going to bump the voltage to 2 VDD minus VTHN. Does it make sense? No? Why? Where? It's not going to anywhere because it's a diode. So it's not going back to VDD. It's going to hold the charge at higher voltages than VDD because it's being reverse biased. Because the capacitor is not like a pure wire, right? It dissipates the charges really quickly. So before you switch it on to VDD, it already gets charged up by VDD minus VTHN across the two plates. Holds the charge over there, right? And now, yeah, you will. Yeah. What do you mean? In which state it will smooth it? It's not.
Like it would charge all the way up, and then as VDD goes to 0, it would start to discharge a little bit, and then it would get bumped back up again.
No, because it swings back to VDD minus VTHN later. So when you switch it back to VDD, it's just adding one more VDD to it. It's not adding VDD endlessly. It's just adding one VDD and then it discharges to this. So it's just going back and forth in between these two states when it's getting stabilized. Just remember one behavior. I think you will be comfortable with this kind of switch. Just remember one, okay? Which is before is, so we're just looking at the very first 0. So think about that way, okay? So you had a like super fast, super short VDD at the very beginning, okay? It's not a super long VDD, just so when you switch it on, it stays at here, for example, okay? And then it drops to 0. This is time 0, okay? It drops to 0. So when it drops to 0, it's going to pull charges from the plate. So that was before the capacitor is getting charged. It had nothing on it, just neutral plate, no voltage difference. Okay, so the very first 0 volts is going to pull charges from VDD to here because the VDD is here and here is forward biased. So it's going to dump charges to the plate that way because you are pulling it to 0 from one side. Okay, so the two plates will be charged up to VDD minus VTHN because that's the voltage exactly here can reach. Okay, and so from here to here becomes VDD minus VTHN. And when you switch it to VDD, it used to be 0, but now you are adding a voltage to it really quickly. So it's like 2 batteries in series you are running here permanently, right? So it's 0 volts. And now you got a 1 VDD and 1 VDD minus VTHN. So you're adding these two voltages together. It's 2 batteries in series. 2 batteries in series. You're adding them together. Eventually, it's getting 2 VDD minus VTHN. And oh no, the power source is not changing. Yes. No. Okay. It's a digital circuit, right? So VDD is actually logic 1. And so after the first half cycle, then you switch it on. And we're getting this voltage. And you switch it off. So this becomes 0 volts, which is exactly like you short this one to ground. Okay, so this doesn't have any voltage drop anymore. It holds the VDD minus VTH here, same. It's the same two nodes. If you probe it from here to ground, you're getting VDD minus VTH. Okay, that's just one stage. You can add more stages to it. So now let's try it. Adding a few more stages. What is this? Again, what is the voltage here? What's the voltage swinging in between? This, right? Mm-hmm. It's very interesting. So it is a oscillation. It's oscillation, but we are trying to get a DC voltage. So this won't be the final output. So what is this circuit though? Yeah, it's a half-wave rectifier because this is a diode, right? Okay. So what is the voltage here will be? You have this one here. It's running through a NMOS transistor. And it's going to have another drop of VTHN. Does that make sense? Remember, every time you go through from the drain to source, you got a VTHN. The amount of voltage drop is exactly the same as VTHN. Because here is now VDD. Okay, so the voltage here will swing in from VDD minus 2 VTHN to 2 VDD minus 2 VTHN. Swinging between these two voltages. Is that correct? Before it's getting filtered out, being smoothed out, right? It's going to be a bumpy voltage between these two values. And the filter will smooth it out, so make it are similar to a DC voltage. We can add more. What is happening to this circuit? We provide a clock to oscillate it. That's a oscillation source we have in the digital circuit. And this is a clock bar, just inverted. Let's see if this makes sense. right? So if you have a clock, so let's ignore this clock first to the following stages. Just look at this circuit. Okay, you got a C2 here, but before we look at C2, what is B oscillating from in between? No, you got a clock. Clock is 0 to VDD, right? Do you agree with that? Okay, now you got another clock adding to it. Exactly, I think that's 180 degrees phase shift when it's getting inverted, right? So what's going to happen to this one? Why you need a phase shift? Well, you cannot directly use the same clock cycle. Have to invert it. So when you are adding a VDD to it, so when this is at VDD, right? When this is at VDD, you're adding a VDD to it. You are getting a high voltage. So at the same time, you want to pull the voltage down to ground here. So it's charging up the cap. So it's getting another VTHN drop from here to here. We're getting this one. And when this is falling, right, when this is falling, and so it's going to pull charge away from the cap. So this will drop to this voltage. And wait. So here is VDD. So if you pull it down, it charges up to VDD minus VTHN. And you adding to it, so you're getting 2 VDD minus VTHN. That's for A, okay? Here you're adding another VDD to it, so it becomes 3 VDD minus 2 VTHN. And 2 VDD minus 2 VTHN. That's going to be the voltage at B. Because you have another clock boosting that one more time. Make sure I understand what's going on for B first before moving forward to the next. So for point A, we're getting these 2 voltages, no problem, right? Right? But since we have another one, which is another clock is bumping voltage to the cap at a 180 degree phase shift. So whenever this the voltage here becomes this, it's going to charge up the cap. Because we're pulling here down to ground, we're pulling charges, so it's going to charge up to here. So whenever it goes across this diode, I think let's do it the same way like as what we did over here. So when it runs across this thing, right? So there will be a voltage drop. So we are going to minus 1 VTHN for each of the peak voltage first. And then because this is also bumping voltage, 1 VDD to it, so we're actually minus 1 VTHN and also adding 1 VDD to it. Right? So that's why this becomes 3 VDD minus 2 VTHN, and and the lower voltage becomes 2 VDD minus 2 VTHN eventually. Because when it goes across the diode, it has a VTHN voltage drop. And when it's being bumped by this VDD, it's adding 1 VDD to it. It's exactly the same concept here, but it's just a little bit confusing. Same to C, right? Same to C. It will have you have to minus 3 VTHN here at C, but I have to add 1 VDD to it, so it becomes 3 VDD minus 3 VTHN and 4 VDD minus 3 VTHN for C3. So I got a 3 here and 3 here, but 4 here. So eventually at the voltage Cn minus 1, here the voltage becomes N minus 1 VDD minus N minus 1 VTHN and N VDD minus N minus 1 VTHN for here. For here, okay? If it runs across this diode again for V out, so V out for V out equals N minus 1, since we're not adding another VDD anymore, right? This is just that working as a filter. You don't have another VDD bumping voltage to it. So this is just a rectifier. So it becomes, it will be filtered out, but the ripple at the very beginning will be this minus 1 more VTHN and no more VDD minus 1 more VTHN. What's the peak-to-peak voltage in between these two? What's the peak-to-peak voltage? Is it getting boosted? Yes, you are getting like N times VDD. If it's 5 volts, you got 4 stages. Ideally, you are getting 20 volts. So instead of swinging here, right, it's just like adding offside to it. So instead of swinging here, you can, if you use this one minus this one, the peak-to-peak voltage is just the VDD, is not changing. So instead of swinging here, it swings here, right? And then you filter it out, becomes a DC voltage. That's how that works. All right. We need the voltage to be boosted because in the sampling and hold, we are trying to detect or hold VDD. And you know that if you only have DC digital circuit, your gate, the highest voltage at the gate is just the VDD. If you don't boost it, you won't be able to pass VDD across the NMOS and get a VDD here, right? You have to boost the VG first in order to pass the entire VDD to the source. So that's why we have to boost the voltage. But we'll look at the sample and hold circuit later on Wednesday. I think for today, we're just trying to understand how the capacitor works in this kind of circuit. So tomorrow we have, is that the last session of the lab or the beginning of the ALU circuit? Beginning of the ALU circuit, so we have 2 more weeks. And after that, we'll have continue working on labs since I have new assignments for you guys to use Cadence. And what's that called? Vim. right? You need to know how to use Vim. It's everything like you deal with on the server. Required. Go to the industry. All the scripts are written in Vim on the server. So better know how to use it. Okay, we'll see you tomorrow in the lab.